All right, welcome everyone. If you've ever wondered how we get massive, stable DC power for really heavy-duty stuff, think industrial motors, big data centers. Well, you are in exactly the right place. Today we're going to move beyond the basic single-phase rectifiers you already know and dive into a much more powerful and, frankly, more elegant solution, the multi-phase Star Rectifier.
So, here's how we're going to tackle this. First, we'll talk about why we even need to look past standard rectifiers. Then, we'll introduce the multi-phase design and actually run the numbers to see how it performs, using a super common three-phase example. We'll also get into its secret weapon, how it handles harmonics, and then we'll wrap it all up with the big advantages.
Okay, so why can't we just use the single-phase rectifiers we're already familiar with for everything, right? I mean, what's stopping us from just making them bigger for bigger jobs? Well, as it turns out, they hit a pretty hard wall.
Look, single-phase rectifiers are fantastic, up to a point, and that point is usually around 15 kilowatts of power. Once you need to go beyond that for serious industrial-level applications, you're going to need a different approach.
So what's the big deal? Why can't we just push them harder? Well, it all comes down to this nasty stuff in the output called harmonics. It's basically electrical noise. And with a single-phase setup, you get a ton of this noise at twice your source frequency. Now, to get rid of that and get the smooth DC you actually want, you need filters that are absolutely massive, super heavy, and really, really expensive. It's just not practical.
And this is precisely where the multi-phase Star Rectifier makes its grand entrance. It is a much, much smarter way to handle high-power AC to DC conversion, and it neatly gets around all those problems we were just talking about.
Let's take a look at how this thing actually works. So on the left, you see the basic circuit, but the real magic is happening on the right. See that output voltage waveform? It's just gracefully skimming along the very tops of each of the input phases. It's like a perfect relay race, where each diode hands off the job to the next one right at the perfect moment.
The best way to think about it is that these diodes are acting like super fast, incredibly smart switches. Each one is just watching its own phase voltage. And the very instant its phase has the highest positive voltage in the whole system, bam, that diode turns on and all the others turn off. It's this constant, seamless handoff that gives us a much smoother DC output from the get-go.
All right, now for the fun part. Let's get into the math. We're going to look at three really important equations that show us, quantitatively, just how well these rectifiers perform and why they are the absolute go-to for high-power stuff.
Okay, first up, the average DC output voltage. Now, this equation tells us something really critical. The output voltage isn't just about the peak input voltage, Vm. It is directly tied to pi, which is the number of phases you have. So what's the big takeaway here? More phases means you get a higher average DC output for the exact same input. That's a huge win.
Next, we've got the RMS voltage. You can think of this as the true power of the output. It's the effective value that takes everything into account, the DC part plus all that leftover ripple, and it tells us how much work this rectifier can actually do when we hook it up to a real load.
And finally, we have the RMS current. Now, this one is a really big deal for designing a safe and reliable system. This tells us exactly how much current each and every diode and transformer winding has to handle. With this, we can pick components that are tough enough for the job and aren't gonna, let out the magic smoke during operation.
Now, these equations are great, but theory is one thing. Let's make this real. We're going to apply them to the most common multi-phase system you will ever see out in the wild, a three-phase Star Rectifier.
So let's run the numbers for a pretty typical scenario. We've got a three-phase rectifier, so our Q is 3. It needs to deliver a nice steady 30 amps at 140 volts to a simple resistive load. Our job is to figure out all the key performance metrics and see how it actually stacks up. So, after we plug Q equals 3 into our equations, this is what we get. The table lays it all out, but let's point out a few things. We've got efficiency, ripple factor, and this one, TUF, that's the transformer utilization factor. It's basically a measure of how well we're using our transformer. A higher number is always better. But wow, just look at that efficiency, almost 97%. That's a massive improvement over simpler rectifiers. It means almost none of the power is being wasted as heat. And check out the ripple factor, just 18%. We're already starting with a much cleaner DC output before we even add a single filter component.
But you know what? High efficiency and low ripple are just part of the story.
The real superpower of the multiphase rectifier, the thing that makes it a total game changer, is how it deals with harmonics.
Okay, I know this equation looks a little scary, but stick with me. It's a Fourier series, and it tells us something absolutely incredible about all that output ripple. It proves, mathematically, that the ripple isn't just random noise. It only shows up at very specific, predictable frequencies, and they are all multiples of Q, our number of phases.
So here's the bottom line, the really crucial point. For a Q-phase rectifier, the lowest harmonic frequency you have to worry about is Q times your source frequency. So for instance, if you have a 6-phase system running on a 60 Hz supply, the very first bit of ripple you need to filter out is way up at 360 Hz, not 120. And trust me, filtering high-frequency noise is worlds easier and cheaper than trying to get rid of low-frequency rumble.
Okay, let's bring it all home. Let's recap the definitive advantages. Why is the multi-phase Star Rectifier the undisputed champ for high-power applications? Really, it boils down to this. A multi-phase rectifier gives us more of what we want, which is a high DC voltage, and a lot less of what we don't want, which is that AC ripple. And the genius of it is how it does that, not just by making the ripple smaller, but more importantly by pushing that ripple to much higher frequencies where it's way easier to deal with. That makes our filters simpler, smaller, and cheaper.
So I'll leave you with a final thought to chew on. We've seen that more phases gives us a better, smoother output. But as engineers, we know there's no such thing as a free lunch. There's always a trade-off. So what do you think is the practical trade-off? What happens to the cost and the complexity of that big transformer as we keep adding more and more phases, chasing that perfectly smooth, ripple-free DC? Think about that, and we'll see you next time.
All right, everyone, welcome. Today, we're going to move beyond the textbook basics. We're going to tackle a really fundamental piece of technology, something that literally powers our modern world. I'm talking about the engineering behind high-power DC conversion, and we'll be focusing specifically on multi-phase Star Rectifiers. You know, think about it for a second. The data centers that power the internet, all of our industrial manufacturing, even those huge grid-scale batteries, all of it runs on a hidden foundation of massive amounts of direct current. And the demand for that high-quality, stable DC power, it's not just big, it's absolutely exploding.
But here's the thing. Those simple rectifiers you first learned about in your introductory courses, they just can't supply this kind of power. They hit a wall, a really fundamental limit. So the big question for us as engineers is, how do we get past that? How do we break through?
Okay, so before we can really appreciate the cleverness of the solution, we have to get a solid grasp of the problem itself. And that all starts with the limitations of your basic run-of-the-mill single-phase full-wave rectifier.
Now this circuit, yeah, it does its job. It converts AC to DC. But just look at that output waveform. That is not the nice, stable, flat line we're looking for, is it? Not at all. Instead, you see it pulsing up to a peak and then, bam, dropping all the way back down to zero. Over and over again.
That pulsing, that up and down variation, that's what we call output ripple. And it's a huge problem. It creates what we call dirty power. It's unstable. Now, to clean it up, to make it usable for sensitive electronics or big motors, you have to add filters. But here's the catch. Because that voltage dips all the way to zero, the filters you need have to be huge, heavy, super expensive, and honestly, pretty inefficient.
So all of this, the ripple and the giant filters you need to deal with it, it creates a very real practical power ceiling. You'll find that for most applications, a single-phase rectifier just isn't going to cut it above, say, 15 kilowatts. And for heavy industry, that is nowhere near enough power.
So, how do we get past that 15 kilowatt wall? Well, the solution is actually pretty elegant. I mean, it's conceptually beautiful. Instead of just trying to fight the ripple with these big, clumsy filters, a sort of brute force approach, we're going to be smarter. We're going to attack the problem right at its source.
And here it is. This is the core idea. Look at that top graph for the single phase. See all those deep valleys where the voltage drops to zero? Now watch what happens as we add more phases. We go to 3, then 6. We're literally using the peaks of the new phases to fill in the valleys of the others. It's a fantastic analogy. It's like turning a really bumpy road into a smooth highway, just by paving over all the gaps.
Okay, so what's the hardware that makes this magic happen? It's called a Q-phase Star Rectifier. The key pieces are 1, a special transformer that gives us Q different phase-shifted voltage sources, and 2, Q diodes,
one for each of those phases. And I want you to pay close attention to how all the cathodes of those diodes are tied together at a common point. That little detail, that's the secret sauce to how this thing works. All right, so how does this circuit actually work? This is the really cool part. What's amazing is that it creates this beautifully simple, completely automatic switching mechanism. You don't need a complex control system, no microcontrollers, nothing. It all just works based on plain old physics.
Here's the governing principle, and it's brilliant. Because all those cathodes are tied together, it's basically a highest voltage wins competition, a natural selection process. At any given instant, the circuit is essentially asking itself one question. Which one of my phases has the most positive voltage right now? And only the diode hooked up to that winning phase will turn on and conduct current. All the others, they're automatically turned off. Simple as that.
And what's the result? You get a DC output that basically just rides the peaks of all those AC input waves. That output voltage, which we're calling VO, is literally just the envelope you'd get by tracing the highest point of all the phases. And look, it never ever drops to zero. The average DC value is way higher and, of course, a whole lot smoother. Okay, so it looks a lot better, right? But we're engineers. Looks better isn't good enough. We need to put some numbers on it. We need to quantify just how much of an improvement we're really getting. And we can measure this leap in performance very precisely.
And wow, the numbers really do tell the story. Just look at this. By going from a single phase to a simple three-phase system, our efficiency skyrockets from about 81% to almost 97%. And the ripple factor, remember, that's our measure of how dirty the power is, it gets slashed from a whopping 48% all the way down to just 18%. I mean, that is a massive improvement for what is a pretty small increase in complexity.
But wait, there's more. The biggest advantage, the most profound one, isn't just that the output is smoother or that it's more efficient. It's actually something a little more subtle. It's about the nature, the very character of the ripple that's left over.
To really get this, we need to pull out a powerful tool from our mathematical toolbox, the Fourier series. You've probably seen it before. It lets us take any complex waveform, like the output of our rectifier, and break it down into its basic building blocks. You get the pure DC component, which is the good stuff we want to keep, and then a whole series of unwanted AC sine waves called harmonics. That's the ripple we want to get rid of.
And this is where it gets really clever. For a Q-phase rectifier, those nasty harmonics don't just show up randomly. They only appear at integer multiples of Q, the number of phases, times the source frequency. So what does that mean? It means as we add more phases, we push that lowest, most annoying harmonic to a much, much higher frequency. So, for a 60 Hz system, a three-phase rectifier's lowest harmonic is at 180 Hz. For a six-phase, we push it all the way up to 360 Hz.
And this is the punchline. This is where it all comes together. Why do we care so much about pushing that ripple to a higher frequency? Because of a fundamental principle of filter design. It is so much easier to filter high-frequency noise than low-frequency noise. In this world, frequency is everything.
And here's the payoff in the real world. Just look at the difference. To filter out low-frequency noise, like that 120 Hz ripple from a single-phase system, you need these big, bulky, heavy, expensive components. But to filter out high-frequency noise, like the 360 Hz from our six-phase system, you can use components that are dramatically smaller, cheaper, and lighter. That is the ultimate practical advantage. It's a total game changer.
Okay, that was a lot. So let's boil this all down into 3 key engineering takeaways. Think of these as core principles you can stick in your design toolkit. First, more phases means better DC. Simple as that. It's the most straightforward way to get a higher average voltage and less ripple right from the start. Second, harmonics are your friend. Well, sort of. Remember, the lowest harmonic is always at Q times the line frequency. Use that knowledge. It's your secret weapon for designing smaller, cheaper, more efficient filters. And third, and this is always true in engineering, it's all about trade-offs. As you add more phases, yeah, performance gets better, but so do the cost and the complexity of your system. You always have to find the right balance.
So there you have it. We've pretty much mastered the uncontrolled rectifier. It's a really elegant, robust system. You just use these passive diodes, and they automatically do all the switching for you, just based on which phase has the highest voltage. It's beautiful. But this leads us to one final, really interesting question. This whole system gives us a fixed DC output, right? The voltage is determined by the AC input. What if we don't want a fixed output? What if we want to be able to control it, to turn it up or down?
What happens if we rip out those simple passive diodes and replace them with controllable switches, like thyristors? Switches that let us actively manage and command the flow of power. Well, that's a whole new ballgame, and that's exactly what we'll dive into next time.